onto this webinar. Thank you very much for spending your time with me. My name is Tim Ward. I'm the CEO of Clued In, and alongside my colleagues at Clued In, we help large enterprises solve complex problems in a modern data landscape. And when we think about data management, it's made up of multiple different pillars. And one of those first pillars is data integration, often thought of as quite a complex part of the overall data management landscape. Now, my goal today is to introduce you to a relatively new concept called Eventual Connectivity. It's a rather modern data integration pattern that we think is absolutely game-changing and taking the data integration world by storm. And really, it's a integration pattern that is built for modern, complex, and globally distributed enterprise companies. So let's head in and take a look at the core problem set that we're trying to address here. So let's be honest. At all your enterprise businesses, your company data is scattered globally across your business. And in some cases, some of these systems are of such a legacy nature that they are fundamentally broken, not allowing you to really easily become a data-driven business and solve this data integration challenge. So let's take a look first at what are the traditional data integration patterns that we're all utilizing today. I think most would agree that the data integration patterns available to us today fall within two main sections. That's either ETL or ELT. And of course, most of you working in this industry will know the E is the export, the transform is for the T, and for L it's the load. And when we talk about ETL and ELT, it's really a rather similar type of pattern. It's just that the ordering of when transformations and loading is done is really offset in the different variations. Now, Clued In falls within the latter, within ELT. Why? And it's probably because of this reason of legacy applications. I mean, predominantly the most customers that we work with are enterprise businesses in the financial sector, the health sector, the insurance sector, and have these types of legacy systems that make it very hard, in some cases close to impossible, to actually work with the source systems in an efficient manner. What that requires is that we need to then migrate or shift that data over to a more modern environment where we can actually process it in the correct ways. If we dive within those sections of ETL or ELT, we really have a main set of protocols that we have available today to solve data integration challenges. And of course, one of the newer players in this area is streaming. It's very much trending, but we need to remember that it's just one of the overall integration patterns, each having their own advantages. If we look at the advantages of streaming, I guess you could highlight that, the fact that it's getting a lot of attention now means it's a great thing. It offers, of course, the ability to offload batch type of, overnight type of processing workloads. The downside, of course, is that majority of source systems still don't support streaming natively. Of course, they will over time, but essentially what this means is that you really can't just have a streaming type of strategy when it comes to integration pattern, especially by itself. Of course, we have CDC, also known as replication, and this is really there to be able to handle those big data movement jobs, migration or replication of data at as fast as possible. And of course, one of the upsides with this is that we can get huge efficiencies going down to the log transaction level, really trying to optimize data movement instead of application logic and functionality. Of course, one of the downsides of this approach is a lot of the kind of leaning vendors. It costs quite a lot of money to actually purchased their CDC support and CDC products. Next, we have messages, and I guess you could also call them enterprise service bus type of data integration patterns. This is quite a good integration pattern. It covers off and checks a lot of boxes. It's the idea of utilizing very similar to batch type of approaches where we ask a source system to query a certain amount of data and we move that data onto a message bus or an enterprise service bus. The value of this is that those enterprise service buses, especially if you're using some of the more modern possibilities, really guarantees that robustness of delivery of data. And this is very important when we're talking about data integration. Batch, of course, still today is the most utilized integration pattern at enterprise customers. This essentially is a schedule-based workload where on a hourly basis, maybe 24-hourly basis, maybe overnight, of course that always becomes harder with globally distributed businesses, that we will go back to source systems and ask for either a delta since the last integration ran, or in some cases we will need to go back and actually get all the data again. This is very much the case with legacy type systems and even modern platforms that don't really have APIs that cater for batch movement of data. The final data integration pattern is a little bit smaller compared to the others, but it's this idea of push notifications or webhooks. Many of the SaaS players today support this type of mechanism where as soon as events are triggered in the source systems, such as the creation of a new customer record, that record can actually be pushed from the source to the targets. In this case, that would be glued in. The overall summary of this is that all of these integration patterns are fantastic to have in our engineering tool belt, and it's a matter of being able to choose the right one where necessary. There is no integration pattern that is the silver bullet. They all have their pros and cons. So, having a look at the good parts of these traditional approaches, I think it falls into two main categories. The first is, well, let's be honest, we've been solving data integration the same way for the last 30 or 40 years, and hence it's well known, these integration patterns. There's many people that have skills in utilizing different products to solve parts of the data integration challenge. And of course, coming with that is there's lots of choice of products. There's open source, there's of course license-based software as well. So that's great. Choice is always a fantastic thing. But let's head into the bad parts. Let's start with the obvious. When we ask our customers, when we ask our partners, and some of these partners are the leading service providers globally, when you ask them how many clients are integrating more than 10 or 15 or 20 different data sources with success, it is very rare that we find an answer of yes. And we're not the only ones that are recognizing this. If you look towards market analyst firms or leading providers like Gartner, they actually say that the predominant amount of clients that they talk to don't have projects where there's more than 5 sources that are integrated across their business. And only 15% of those same clients have around 15 or more data sources being unified into a common fabric of data with these traditional approaches. And that for me is quite eye-opening. When you look at the average enterprise, you'll probably note they have at least hundreds of systems, and especially with some of the older financial institutions, they have thousands of different systems that contain their company data. Now, for those of you who have worked on integration projects before, you will know that there's always this ramp-up time, typically many months, where we have to ask all the data architects from all the different systems kind of jump in a room together and draw on a whiteboard of how all their systems kind of are linked together. Now, I'm going to do my best to play the devil's advocate here, where I'm going to give the traditional approaches the benefit of the doubt. In that case, as long as I kind of give them the benefit of the doubt, it shows that we're trying not to be biased in our approach to data integration patterns. So you can probably imagine that based off this long amount of months in figuring out how all these 5 different systems connect together, it's going to require the data architects or domain experts in each system to really figure out and draw up a mesh of how their one system connects to the other 4. You can probably understand why this takes so long. The other part about these traditional approaches is that it genuinely kind of forces us into a model of fitting a square peg into a round hole. Let me explain. How most businesses are addressing their data integration challenges today is that they are upfront specifying a perfect model of what they would like their data to look like and how it would be related. And then we ask the source systems to somehow fit into that perfect model. Now, what you'll find once you take on these larger integration projects is that this does not work. It does not scale. Even for the small amount of systems like 5 enterprise platforms. Now, of course, based off this, during these ramp-up months of planning and whiteboarding sessions of figuring out how all these systems integrate with each other, I will admit you'll often find that domain experts for their own system. So, you go to a large bank, you will probably find someone who is a domain expert of the transaction system. Now, whether they have hundreds of tables, tens of tables, thousands of tables, I'm going to give them the benefit of the doubt that you'll still find a couple of people that will be domain experts on all of those tables. In reality, it's probably not like that. In reality, what we find is that the core people that are behind those systems have moved on to other positions, and you've had people that have had to come in and learn those systems. So although they are the domain expert at that enterprise, there's probably still some lack of knowledge on exactly how all of those different data sources within the same system, whether it be tables or files, how they interoperate with each other. However, we're talking about integrating multiple systems. And it's very rare to find domain experts that actually know how 2 different systems connect. But once again, I'll give the traditional approaches the benefit of the doubt. Maybe we can find people that do know those different systems and know how they all connect to each other. Of course, with the traditional approaches, what we're actually doing is we're pretty much 100% relying on humans finding the connections between not only their own system, so from one table to another table within their own domain, but we're also relying on humans to be able to make that leap between different systems. And this is really where the complexity starts to grow. But this is not where the bad parts stop with the traditional approaches. The traditional approaches of data integration forces us into this pattern where we believe that systems can talk well point to point, directly with each other. And this is rarely the case. Let's take an example. We have a CRM system like Salesforce, we have an ERP system like Navision. It's very rare that the objects that exist in those systems will be able to connect together from Salesforce to Navision. It's quite often that you need to jump through other systems to be able to figure out the links and the keys so those systems can start talking to each other. If you look at the tooling that is available to us today as enterprises to build our ETL or ELT pipelines, whether that's using streaming or batch, that's kind of not really a necessary detail, but essentially most of these vendors are providing drag and drop interfaces to be able to build these data pipelines. And I can guarantee you these tools are fantastic for simple situations. It's essentially targeted at allowing semi-technical people to build flows. For the types of challenges, of course, that we see at large enterprises, this breaks down pretty quickly from a scale perspective, and especially from a maintenance perspective. The other part about the traditional approaches is that they work under this premise that systems will be static in nature, in that if we get those architects in the room today, well, if they are able to figure out those links and IDs between the different systems, that, the problem solves, that we won't have to constantly address how these systems are connected. And the reality is with the kind of enterprises that are really in modern day data management spaces, they're constantly growing, whether that's through new tooling or more likely through mergers and acquisitions that bring on brand new data sources, and we need to figure out how those connect into our world as well. You can probably imagine that the average company, if we're being generous from an enterprise perspective, let's just say they use 100 tools, where in reality, in some cases, it's usually thousands of different systems. But let's just still go with that the average enterprise uses a couple of hundred different source systems. Even with that, the thought of being able to integrate those 100 systems in any type of efficient, quick manner is just really not realistic. After all, we're talking about even 5 systems enterprises are finding complexity with. And we have not only some of the biggest service partners in the world that are reiterating this, but even market analysts leading firms like Gartner that are backing this up with raw statistics. One of the other interesting parts that you realize with these kind of traditional techniques of integration is that every single pattern that we have available to us as engineers actually makes the assumption that your data is clean and ready to be blended between different systems. This is one of those cases where I'm no longer going to play the devil's advocate, because really every single customer does not have clean data. Every enterprise has data quality issues. And I can confidently say that 100% of the time, data is not ready to integrate between different systems. There is quite a lot of data preparation, normalization that needs to be applied, and cleaning mechanisms to get it to a higher possibility that records will blend across different systems. We also have to look at the history of these integration patterns. I'm a firm believer that the patterns that are available to us today worked well in a small data world. After all, a lot of these patterns were designed with specific use cases in mind, the data warehouse being one in particular. And so a lot of these designers, a lot of these systems that we used in the past or are still utilizing today with these traditional approaches, they were actually designed with specific data pipelines in mind. Unfortunately, there are many more types of targets that require a much more modern approach to data integration. So before we head on to the solution to this and talk about the new, more modern integration patterns that are available for us today, I want to highlight the core challenges with the way that data integration is being solved today. One of the core pieces is that the traditional methods that are available to us today require that you know a schema or a model up front that all of your data sources need to abide by. It's that classic idiom of a square peg in a round hole. It also makes this assumption that you can easily identify the keys, the IDs, the foreign references of how different tables or sources of data connect to each other, even in the same system that is complex. When you start to do this across systems, you start to realize this is one of the hardest challenges in the data integration space. One thing that becomes very obvious as well is that a majority of the integration patterns actually are quite oblivious to the fact that in many enterprises, there aren't IDs that are available. And there is the need to join across different systems in a slightly more fuzzy type of approach. A lot of these integration patterns rely on the fact that we have perfect IDs that exist across these different systems. And 100% of the cases that we have worked with, this is not the case. So let's touch on that for a little bit. When we're talking about fuzzy merging, there of course is some type of risk factor that comes in. We need systems to be able to give us confidence that we can actually merge records or find the links between records in different systems in a statistically confident manner. One of the things that you'll find about the common day mechanisms that we have today is predominantly most of the leading vendors are taking quite a naive approach to being able to fuzzily merge records across systems. I can tell you straight up how most companies are solving this today. They are using either probabilistic matching functions or string distant functions to take two records that are suspected to be duplicates side by side and doing comparisons of how close the string values are against different properties to each other. Let's take an example. If we found that we wanted to merge companies across different systems, and we found that the names of the company had a difference by one letter, and that the address had a difference maybe of 3 letters. Maybe the postcode was in the wrong order, in a different order between these two different records. Essentially, we then apply weights to this system that say, listen, I would accept a difference of 1 in a name and 4 in an address. And you can probably start to imagine the amount of issues that come up with that type of system. Although these functions are still important to run and very much clued in, we still do run these, it's only one of the necessary steps to be able to merge records in a valid and confident manner. One of the things that we always forget as well with this particular problem is that when we are looking at two records side by side, what we're completely missing is the context of those records. What are the other records that are connected to that record, either directly or indirectly? And that's really where the magic starts to happen. That's how we can start to look into finding linkages over different data sources in a very high statistically confident manner. Of course, a big piece of the ETL process is figuring out how different objects correlate to each other. Whether it's figuring out if two records are the same, or if there is some type of referential integrity that lies between two objects within the same system, or maybe across systems. Now, when you think about the way that it's done now, we often have to rely on being able to choose the different types of joins that would get us the result that we need to, figure out if we have a link between two different records. If we take something like the set operations that are available in the predominant amount of SQL-based databases, you'd be looking at inner joins, outer joins, right outer joins, and the list just goes on. Now, Clued In actually utilizes a different type of database for this part of the process, for figuring out the model and for figuring out how records join across different systems. That database is a graph database. And when it comes to joins, there is only one type of join that exists within a graph database. And this just makes this entire process that much more simple. So let's head on to the solution. Let's head on to the new type of data integration that can solve modern types of data integration requirements. I'd like to introduce eventual connectivity. It's a data integration pattern that works for modern global enterprises and scales for modern needs. Let's have a look at how it works. Let's start with the business advantages of taking this approach. Remember before when I was saying that usually in integration projects, there's around a couple of months, if not a year, of upfront work and planning to figure out how all the systems bind together. It requires all of those data architects to get in that room and talk and battle it out to figure out the IDs that join their different sources. Well, with the eventual connectivity pattern, this completely goes away. The pattern allows you to integrate one system at a time. And actually, to go into more detail, you can even be much more granular. You can integrate even one object within a system at a time. So what this means is that although we need to talk to the domain experts, we don't need to have those upfront architecture meetings across domain experts. Because let's be honest, even though it's probably relatively easy to find the domain expert of one system, it's extremely rare to find someone at an enterprise business that understands domains across two systems. The other piece is a business advantage, is that there's no need to identify how objects join within the same, or even better, across systems. So when we interview these domain experts, what we don't want or what we don't require is to ask them, how does the people table join onto the company table? And that is wildly advantageous because suddenly we can let technology figure out how these records are linked. So how can it do this? The good thing about the eventual connectivity pattern is also that it's very simple. There are two base requirements that are necessary to achieve eventual connectivity. The first is the realization that the goal of eventual connectivity is not to fit a square peg into a round hole, but rather for a system or a machine to tell us what is the natural shape of the data sources that you are integrating. For this to technically work, we need to rely on technology that has certain requirements. One of those is we need a database that can support persistence, but not require an upfront schema. Why? Because we don't know what the schema will be upfront. We don't know what the natural model is of the 5, 10, 100 integration sources that we are plugging in. So fortunately, that already gives us quite a lot of choices. You'll probably know that most SQL databases do not require a schema up front. Good examples would be Solr, Elasticsearch, Mongo, Neo4j, etc. The next requirement is that we need it to not require a schema, but we still need it to scale. That requires that we have a data store that can support classic scaling mechanisms like indexes and constraints. Well, the good news is that all the data stores that I mentioned before all have that support. So I still have many different options that are available for me to solve this challenge. So finally, we need a data store that can support the fact that we will need to project interpretations of this inferred model at high speed and efficiently. And let me describe that another way. The goal behind eventual connectivity is not to model your data into the final modeling. It's to provide flexible modeling that is inferred from the source systems. Now, because of this then does filter that list of supported data stores down to a core group. And that is the database family of graph databases. To be more specific, graph databases that can be schemaless in model. It is worth mentioning that there are graph databases that still do require schemas. So we need to choose one, and there are many, graph databases that can be schemaless for models. We then actually need the data integration that can support the ability to map into this persistent store, as we've alluded to, needs to be a graph, one object at a time. And there are 4 very important components to support this. The first is unique codes, so unique identifiers for objects. The next is edges, very similar to foreign keys or references, but just with a slight advantageous twist. The next is aliases. We'll go into that in a moment. And finally, we have vocabularies. So first, let's look at the unique codes. Unique codes will be universally unique identifiers. So when we refer to unique identifiers universally, we mean that this record is absolutely unique across source systems and even across clued-in accounts. So even if we were to plug in the same source system into 2 different clued-in accounts, that they would have their own unique identifier. Because of this, of course, we can't just use IDs. And that's why these unique codes are made up of 4 separate components that guarantee universal uniqueness. Luckily, a lot of these components, or at least 2 of them, can be inferred. The other 2 require you to map. A type would be the type of object, whether that's a domain like an organization or a person or a task or a document or a ship. The other is the ID, so the identifier that is unique to that object. Based off this, we can go through a process of identifying the unique IDs on a particular object. In many cases, you might have more than one. The next is edges, and this is really the key behind the eventual connectivity pattern. Edges are your way to instruct clued-in that you have an object that has a property or a column or a value that is pointing to another object. The key with the eventual connectivity pattern is you don't need to tell the pattern where that object is, whether it lies within a table within the same system or maybe within a completely different system. So edges have an optional type, such as a relationship type. I'll give an example. We have a person that's pointing to an organization with an optional type to describe the relationship. It could be that a person works for that company. But what is necessary are 2 components to construct an edge. The ID of that target item and the type. So for example, if we had a person table that had a property or a column called organization ID, all we need to do is flag that this organization ID is an edge to an organization with this ID. We don't need to tell it which table or tables or systems that it could actually find this same ID in. That is the key behind the value of the data integration pattern, is that it can figure out for you what other systems or tables this ID exists in. And what we found with our customers is that often, unless you're using systems like RPA, robotic process automation, where you're pushing IDs around to different systems, which, to be honest, is quite rare that we see that IDs are being pushed around. It's often that you might need to look to online or open data sets to be able to fill in IDs to jump across systems. But this eventual connectivity pattern will be there that if there's a link, it will find it without any human interaction. The next important component is aliases. And this is your way to instruct that there is a property that could fuzzily lead to a linkage between the same system or over different systems. The good thing is we can keep it simple. Like other vendors, we don't need to set weights or probabilities. It makes a simple mapping process that is maintainable and adaptable. I'll give an example. A company like Clued has multiple different aliases. Our full reference is Clued APS, but the different global businesses that we have their own aliases. Clued Australia PTY. These all are essentially referring to the same mother company. However, they are their own legal entities. This is still an alias for the same company. And finally, we have vocabularies. Vocabularies are your way to map properties in source systems into a common vocabulary. If you do this, Clued can essentially understand what the mapping is, and that's really where the magic kicks in. I'll give an example. We might find that in our CRM system, we have a field for our contacts called job position. Maybe in an Oracle database, it's called job title, and maybe in our HR system, it's called something completely different. Our goal is to normalize and standardize that vocabulary into one common vocabulary. And this becomes important when we actually want to utilize the data sitting within Clued. It simplifies and abstracts away the source systems so we can just work with data in a much more abstract manner. The vocabularies are also key to be able to bridge data across systems. I'll give an example. If we find that we have an identifier in Salesforce for a company, which is the Salesforce ID, it's probably very rare that you'll see that ID in any other system besides Salesforce. However, if we were able to enrich that record in Salesforce, look up the local business registry and find the business ID, and then did the same over in the Oracle system, as long as we map that into the core vocabulary for the local business ID, Clued can then create entity codes out of that, or unique codes. And as we saw before, unique codes are your ways to be able to bridge data across systems or even within the same system. So where does the name Eventual Connectivity come from? Kind of very similar in nature to the eventual consistency of the database world. It's this idea that eventually at some point in time, we will be able to find a link between records. Until that point, we construct what are called shadow entities, or also known as floating edges. Now, these are records that get constructed off edges. So I'll give an example. Imagine we have a person object that has an organization ID property on it. We've instructed that that is an edge in the system to an organization. But really importantly, we have said, I don't know where that organization is. Clued please figure that out for me. Now, based off this, what we will actually do is put one of these shadow entities or floating edges into the persistence store. Imagine it thinking there as, okay, I've got a reference to an organization that has this ID, but I don't have a target. I don't really know where this is. Until we actually go to map the organization table, that's when we ingest it. It will say, hey, I'm an organization with that same ID. That means that we can eventually connect. Now, floating edges also have a real other advantage, is that often we don't know where these other tables or systems exist. What floating edges do is make it very obvious that there is a link to a record that you have not ingested yet. When it comes to things like companies and people, that will really help point to what system you should actually ingest next. I just want to reiterate that although most businesses do want to fit their data, their source systems, into the perfect model, that is still a fantastic idea. In fact, a lot of businesses that we work with in certain industries are required to model their data. This is financial services, insurance companies. Sometimes it's actually regulated. They need to hit a certain model in the way they store their data. But the premise and the intention of the eventual connectivity model is to infer the model from your sources in a scaled way that will easily allow you to project that data into your perfect model. So in this way, we get the best of both worlds. Clued-in offers the flexible access to data in any model that you want, knowing that we can have those use cases such as an MDM system where we project the data into the perfect model. But there will be other use cases where we don't want it in that particular model. So having that flexibility is really important. So does this scale is a really good question. Well, when you think about the type of database we're utilizing to persist the connections and modeling of your source systems, we utilized a graph database for this. Graph databases were designed from the ground up to run joins as fast as index lookups across huge amounts of data. For example, if on request of data into an MDM system, we might actually want to project this inferred model into the MDM environment. Maybe it's a SQL database. Now, that's fantastic because we know the model and we know that relational databases require a schema. So we can construct that perfect schema in our SQL database, and we can project that perfect model out of the graph store to fit into that model. One of the languages that makes this very easy is GraphQL, because it abstracts all the complexity of the projections away from the user. It also can facilitate that ability to optimize the queries to run as fast as possible. So I'll give you an example. Do you want to project a graph into a relational model? Not a problem. Want to project a graph into a flat table or document? Not a problem. Because the graph is the highest fidelity data structure or way to model our data. What happens if we wanted to do it the other way around? What if we had our data in a relational store and wanted to project it into a graph? That's when we have issues. That's when we need systems like Clued-in to be able to build graphs automatically off source systems. Now, to touch on the vocabularies for a moment, the importance of this is that it allows us to abstract away the source systems to talk to your data. So instead of asking a system like Clued In that you need all of your customers from Navision and Salesforce and Dynamics and ServiceNow, and here are the specific keys to join those records. The good thing in Clued In is that that's already done. All of the records already have the connections. And instead of talking about systems like Navision and Dynamics, I would much rather just say, I want our customers. I don't want to need to keep track of where those customers exist. That is the problem that exists today with siloed systems. So the Clued In vocabulary allows me to achieve that. The other thing that we often forget is that companies don't stand still. They acquire new tools, they acquire new companies that have their own set of tools. And so the eventual connectivity pattern is designed to be able to make it very easy to bring on new systems in an easy way. Why? Well, it comes back to that core design principle that we can map one object or one table at a time without having to think about the other systems. So there's no need as we acquire new tools or new companies to meet with all of the data architects in a room and figure out how all these systems work together. Not to mention that imagine having to try to build those pipelines for 15, 20, 50 different systems and then come and revisit that after 6 months. Just trying to figure out what were the decisions that were made that built those pipelines does not scale. So one of the key last points I'd like to touch on is what about performance? One of the reasons why we model data is because we want to be able to achieve scale. A good example would be a data warehouse. The reason why we model data based off dimension tables is that we want to run reports off billions and billions of records. And with flexible modeling, there is always some type of hit that you want to take. And of course, that will typically be performance. We have to remember that eventual connectivity is not designed to be the fastest way to move data from one system to another. It's tackling a completely different part of the overall data integration pipeline, which, let's be honest, is the hardest part, figuring out how data connects. That being said, once data is actually persisted into Clued In, it is immensely fast to pull data out of the system. Obviously, the fact that we index and filter and look up via keys is all indexed in a way that makes it super fast to be able to leverage data out of us. So I hope you were able to learn about this new eventual connectivity pattern and the values of and advantages of taking it into consideration. I look forward to hearing more questions on the webinars, and I wish you all a great day, a great morning, and a great night.